Yes, if Justin share the screen, I will. I want to thank you, Aaron, for putting this together. You and Michael and Hannah, and I think your topic is very interesting. I think we are afraid of of contact for good reasons, but I think that there is a lot of potential here, and we're also going to talk about um, um, Chungmin Kim and Justin Kerr are going to talk about two projects from our lab that address aspects of this. One being the deformability of these contacts, the gripper pads in particular, and the other is looking at tactile sensing, and particularly relates to the problem of aliasing that Maria just presented or alluded to. And I want to very quickly say that we are looking for postdocs in our lab. So please email me at goldberg@berkeley.edu if you're interested in a postdoc. And with that, I'm going to do what good advisors do, which is get out of the way and let my students present. Thank you.
So I'm just gonna use this mic if that's okay, right? Good morning, everyone. Nice to see everyone here. I'm Justin, and
I'm Chungmin.
we're going to present on two projects on contact and manipulation. So the first project relates to this idea of touch and vision synesthesia. And what this means is the ability to kind of see one sense through another. And humans have an incredible ability to visualize what something feels like and what something looks like based on touch. So we know that this corner is sharp, and we know that my shirt is soft, even though we've never actually felt either of those things. So at a very early age, humans start learning this incredible ability just by unstructured interaction and play with the world. So babies are constantly putting things in their mouths, they're constantly touching things, and that link between two different sensor streams of their vision and their touch allows them to learn a lot of grounding about what things look like and what things feel like. And so the primary question that I'm going to be kind of dancing around in this talk is, can we build a similar association between touch and vision in robots? And in particular, we want to do this self-supervised, because the less input we give to the robot, the easier it is to scale, the easier it is to put on new platforms, and et cetera. And then to fit into the theme of this workshop, can we do this by bumping into things? Because the more unstructured the data we gather, the more broad things that we see, the better the more diverse interactions of the world, the better associations we can learn between touch and vision. So I'm going to take a brief aside on what I think is the power of multimodal learning, where we learn from two different synchronized data streams. So this is kind of a brief visualization of CLIP, which I'm sure a lot of people know of, but I think the central idea of CLIP is that it's a model which has learned association between images and language. And the way that this works is we take a boatload of data from the internet, we dump it into this model, and it learns an encoding of language and an encoding of vision, which learns to associate the two ideas. So here's just kind of a quick schematic where we have a text encoder and an image encoder, and doing training, all it's doing is basically learning to associate in a large batch which pairs correspond to each other and which pairs should be far apart. And this has some absolutely mind-bogglingly good results, where just giving it tons and tons of data, you can actually backwards generate images from that embedding. And this is the paper called Dolly, also from OpenAI. So this is just an idea of like how powerful unstructured real-world data is. But I guess the question here is, how do we get all that data for tactile manipulation? How do we get unstructured real-world data for this kind of task? It seems almost impossible. Well, one idea is SimReal. This figure probably looks really familiar to you. This is some awesome work from Maria about tactile localization with SimReal. And so I guess we've already seen this briefly before, but the idea is like if you have a large data set of sim to real depth, you can get really strong real world performance using on tactile in-hand manipulation. And here's another cool work, which comes from Stanford, called Object Folder, which is a similar idea of like multi-sensory data sets where we have a bunch of simulated objects and then they produce data of vision, audio, and touch. And I think the challenge in sim-to-real is that this works quite well on smooth surfaces using depth, but it's really hard to capture subtleties like texture. So these kind of methods would be hard. So it would be hard to train something like what the seam of my shirt feels like, or what the difference between a smooth metal surface and a textured carpet or something like that. So then another idea is maybe we can just use the physical world as kind of self-supervision. So here's the work from vision literature. I think it's really cool where they train on unstructured videos, basically on YouTube. And the task they're trying to do is align audio and vision. And the cool result here is that even though it was never trained on localization, they're able to kind of probe this network. And given the sound, the network is able to predict in what part of the video the sound is coming from. And so I think this is another story of large unstructured paired data can get really interesting representations under the hood. Okay, so now going a little bit closer back to the theme of this talk, which is contact localization in towels. So here's some really cool related work on tactile imaging and vision on cloth. So on the left, they took a large data set of what images of cloth looked like, and then also what those same cloths felt like. And the cool part about this paper is that given the tactile imprint of different cloths, they could actually kind of predict what the physics of the cloth behaved like as they draped along the surface of a table. On the right, I think, is the work that's kind of inspired this one and very similar in spirit, where they have a static mounted camera of a robot, and they take a video of the robot touching a lot of different objects on a table. And they're trying to learn to kind of go between what the touch feels like and what the robot is touching at the time. And they're able to learn kind of a mapping between the vision and touch from unstructured data. And so one key point I want to kind of argue for here is that I think that data sets for tactile and vision need spatial correlation. And so what I think these two are missing a little bit is that the perspective of the tactile image and the RGB image are extremely different. So if we want to do things like precise localization, I think it's very hard for these. And so now I'm going to talk about some kind of a physical instantiation of what I've been talking about, planar contact localization on towels. So we're using a digit sensor, which is a tactile sensor very similar to the gel site from Facebook. And here I'm going to talk about a little bit about our self-supervised data collection pipeline. So we have this camera rig, which is designed for taking spatially correlated data. So we have a camera very closely connected to a tactile sensor, and they're right next to each other with a calibrated distance so that we know how far, what the distance is between them. And the way that we use this is we put a bunch of surfaces on the table in front of it, and the robot just kind of stamps it down on the table, collecting paired images of the cloth as well as the tactile readings. And so here you can see an example where if you see an edge of the cloth, there's very clearly an edge in the tactile reading. And if you see just normal texture, it's just the tactile texture. So it's very closely spatially correlated image texture and tactile texture. And then we have a kind of simple contrastive training pipeline, very similar in spirit to the boatload of data from the internet, except our data set is much smaller. What we do is we throw all these images into an image encoder, we throw all the tactile readings into a tactile encoder, and then we train them on a contrastive loss, basically the same as what the clip contrastive loss was, trying to predict which pairs match with each other. All right, so now I'm going to briefly describe some cool things that we can do with this. So here's just a very quick visualization of like kind of what the validation looks like in just the training set. So each one of these rows is a batch of 16 images. On the left, we have the input RGB image, and on the right, we have a bunch of tactile images. And it's ranking the similarity between the input RGB and all the tactile images. And so the one quick thing to take away from this slide is that the top two rows have very flat textures and the bottom two rows have edges. And if you look in the tactile images, if you give it a picture of an edge, the tactile readings all are edges or corners or things like that. And on the top, if you give it a flat surface or a textured surface, the tactile readings correspondingly are flat or a dull texture. So the task that we want to apply this to is contact localization in an image. So if I show you this tactile reading, if you look carefully, it's actually of the corner of a towel. And so we'd like to be able to kind of generate a heat map over this image of where this tactile reading might be, and hopefully it should line up with the corner. So how do we do this? This is actually really similar to what Maria described with depth image localization, except in this case, we're going to use the RGB image. So we break this image into a bunch of patches and feed it into the image encoder. And then all we do is we rank the similarity of all those patches with the tactile reading. And we get an output heat map that looks like this, where the brighter yellow, the more similar to the input image. So in this example, you can see that it actually does light up more around the corner, which is good. And also, interestingly, it lights up on the edge of the towel as well. Okay, so here, just to touch on some more examples. So here are some examples with things that it was trained on. So a set of towels. In the first row, if we touch the edge of the towel, it learns to associate that the edge lights up a lot more than the inside or the table surface, because it's kind of picking up on the edge-like features. And if we touch the inside, like on the bottom row, then you can see that the heat map is really highly lit up on the inside of the towel. So instead of edge texture, it's kind of picking up on the inside towel texture. Interestingly, in the middle, it's touching an edge between two towels, but it's only highlighted along the edge between the towel and the table because it hasn't pressed deep enough to see the towel underneath the first towel. There are some unseen cloths. So in the first two rows, it's touching kind of in the middle along an edge. What's interesting is that in our data set of towels, there's no edges in the middle of cloth. So it thinks it's touching along the edge of the cloth rather than inside the cloth because it's never seen things like that before. The second row is kind of a success case where it successfully localizes the touch or along this crumpled rim of the cloth. And then the bottom is another kind of success case where it's kind of learned to match this dull high frequency texture with the tactile image again. Just really briefly, here are some totally out of distribution materials. Vertical cable, horizontal cable don't work very well because it hasn't seen anything like that before. I think another slightly interesting result is that if you touch a smooth metal surface, you can see that it sort of associates that texture with this smooth table beneath it, because during training, it's felt smooth things before, and so it thinks it's the table. So going forward, this is where the bumping into things comes in. We really want to try to supersize this data collection by just unstructured grasping objects or touching things in the environment. Ideally, we should be learning from videos rather than paired images. So the more wild the data, the better. So we want to go from like a very structured setting where we're just stamping images and maybe just collecting freeform videos like Ego 4D dataset, things like that. And then applying this to more interesting tasks like 3D contact localization or rummaging in bags to localize objects and things like that. All right, so I'm going to hand it over to Chungmin to talk about grasp simulation.
Hi, so today I'll talk about some of the work that I presented in ICRA about IPC-GraspSim, which uses a computer graphics simulator to help bridge the sim to real gap for grasp labeling. So just kind of taking a step back to what robot grasping is. When we grasp an object with a gripper, the gripper is interacting with the object, bumping into the object, and continually changing the contact that the gripper is making with the object. And how do we typically try to train systems that learn to grasp? Some of the prior works have leveraged physical labels from robots and human annotations, but these are pretty expensive to get. So what a lot of people have worked on is how do we leverage simulation in order to collect these data sets? But some of the core issues that we faced with these data sets is the distribution shift from the simulated data sets and physical grasps. So looking at the slide, what we get is given an initial state of the object pose and the gripper pose, if we are to use a grasp metric that does not consider the dynamics, which are frequently used because it's easier to compute, it's faster to compute, and it's easier to scale up for large scale data sets. Without dynamics, we can falsely predict some grasp as successful while it fails, and this is pretty catastrophic if we want to learn good grasps. On the other hand, one issue that we face with rigid body simulators such as PyBullet is sometimes contacts can give really erratic behavior, such as this GitHub issue here. And the solution to this one was something like, oh, have you checked the mesh, which is not good if you want to scale it up to multiple types of objects that you want to have in a large scale data set. So something that we can think about is like, oh, what if we just use dynamic robot simulators to consider the dynamics, and also something that can support soft body simulations so that we can avoid using these rigid contacts that can give erratic behaviors. So we have this really kind of simple, possibly a simple solution to like these generating good grasp labels for data sets. And if we can get good data, then like maybe we'll have grasp with less sim to real gap. But the biggest issue that we face here is that a lot of soft body simulators can give bad labels if we don't train it right, or if we don't tune the parameters correctly. So one of the issues that we face with dynamic soft body grasp simulators is that if you don't tune the parameters correctly, then you can face interpenetration issues with soft body simulators, or these force field effects if you don't tune the collision distances correctly. And when we test arbitrary grasps on objects, such as this object in the screen, with improper tuning, it can kind of jerk these objects up or kind of interpenetrate with the gripper, which can lead to visually incorrect grasp, but also just incorrect grasp labels in general. So how can we simultaneously and robustly model dynamics and contact during grasping? What I propose is that we can use some of these high quality grasp, high quality computer graphic simulators to simulate contact. And this work is from SIGGRAPH, talking about how they can simulate these interpenetration-free contacts even during large contact forces. And what I propose is, can we just use these kinds of high quality simulators to use for robot grasping, where we know that high quality contact simulation is important. So here I propose IPC-GraspSim, a robust compliant gripper simulator that uses IPC as the physics backbone. So I do a quick, I initialize the grasp, I close the gripper, and I lift up the object. And based on whether this lifting is successful or not, I do a binary grasp success metric. And I average this over multiple grasps. So visually, comparing it to an IPC-GraspSim baseline, it visually returns a grasp, but it is also actually correctly lifting up the objects as we expect in the physical setting. And if we look at this over like a set of grasps over a variety of grasps, we see that visually there's like a high correlation observed between this novel simulator and physical experiment labels. And comparing it to some of these quasi-static grasp models and the soft body simulator IPC-GraspSim, we observe a higher general sim to real difference between physical setting, but with a significantly high runtime. And some of these are failure modes that we observe in the simulator, which is due to some of the issues, just a lot of model mismatch errors, and that's very related to some of the key problems and next steps that we faced in the simulator, which is, hey, this work is really interesting, but how are we going to scale this up? How are we going to tune the parameters for the simulator? And we've been currently working on addressing this issue by using a higher speed simulator that still guarantees this contact interpenetration free constraint. And all of these are running significantly faster, on the order of hundreds of times faster than IPC-GraspSim, which is really exciting for scaling up. And we hope that we can use this to generate the database and train the supervised models for grasp learning. And that's kind of thank you for listening.
If there's time, happy to take any questions people might have.
Thank you for the great talk. So you mentioned sound earlier, and then it didn't kind of loop back in. And so I'm wondering, either in simulation or, sort of just our understanding that sound is sort of encoding some of the contact itself, even on a towel. If you listen carefully, you might hear a little thud. What is your thought on the inclusion of sound in these approaches?
Yeah, I think sound is really interesting because it's a very easy sensor modality to use. You can just tape a microphone onto the gripper or something. We haven't personally investigated, but I think it would be really cool to have as many data streams as possible integrated into a system. So I know that there was a paper here about using sound for localizing objects inside a bag when you hear like keys jiggle when you touch them or things like that. So I definitely agree that I think sound is an underexplored aspect in robotics that can have a lot of rich contact information there.
Hi, thanks for the talk. This is really, really exciting. I have a question about the soft body dynamics simulator. So um, soft body simulations are insanely hard, especially when one tries to actually get good contact models, slip and friction and things like that. And I'm wondering, for this particular software package you have set up, how much do you think some of the failure modes you observed are due specifically to the geometry of your gripper versus sort of like maybe if the gripper instead was fully soft? Like, is it the case maybe that having these very rigid jaws is creating part of the problem?
So most of the failure cases that I addressed was it was mainly with regards to how well can we match between what we observe in simulation versus in real. And for this project, we particularly investigated these rigid grippers. But I do think that with soft grippers, a lot of these like bouncing around within the gripper, pushing motions, and all of these dynamics would look very different for soft grippers. And I think that would also be very worth investigating as to how soft grippers might be able to solve some of these sim-to-real gap issues as well.
Again.